Hello and welcome back. It is me again, and today we're gonna be introducing quantum mechanics. And get ready for Eve. That was pretty good. I'm pretty happy with that. I'm not too happy with this. I am nonplussed. Nonplussed, I say. What am I gonna do with this? I am a fool. I am always a fool. Do I use my razor blade? I it's risky. I could die. Actually, I will die. Well, no, I'd have to use the fool. I would otherwise die. Yeah. Go get him, bird. Oh. Well, that was anticlimactic. Oh, I could have saved that with the fool. I guess I am still a fool today, because it is the same day as yesterday today. Can you believe that? Well, it is for me, because I'm recording these on the same day as yesterday. Funny how that works. No. Yes. But we are indeed introducing quantum mechanics today. It sounds a bit What? That was a combination of words that were never meant to be combined. Ridiculous and ludicrous. Ludicritous. But that is simply the nature of this series that I'm doing, where I like to talk about topics and learn things, and maybe force you to learn some things too. Isn't that fun? What a great start. I mean, not amazing, but great nonetheless. Wow. I'm impressed. I just need a trinket. Nice. I will first introduce quantum mechanical concepts in the abstract sense before... Yeah, this is a great start. I mean, you know, I guess I'll take it. Before moving on to a more in-depth summary of major topics. So broadly speaking, quantum mechanics is the fundamental theory in physics that describes the behavior of matter and energy on the smallest of scales, typically at the level of atoms and subatomic particles. Here are 6 key concepts in quantum mechanics. Number 1, particle-wave duality. I may have talked about this before. I mean, I did do a fairly early episode on the dual slit experiment, I remember that. So that's close enough to say that I've talked about this before, I think. I am scared of this room. I am less scared of this room. I don't know why I was scared of this room. I was really just afraid of whatever that champion enemy was gonna do. And then he did nothing. Like a coward. Just checking for health, because I'm not at full health, and then before saying that, but after I entered the room, I realized, wait, I don't want to be at full health, because I'm Eve. You know? Bye-bye. And there's simply nothing out this way. Cool. Get him. Get him. Cool. So, particle-wave duality. Particles such as electrons and photons exhibit both particle and wave-like behavior. Both particle-like and wave-like properties. For example, electrons can create interference patterns, a wave phenomenon, when passed through a double slit apparatus. Refer to the double slit video for more information on that, I suppose. Although, again, we will... I'm not sure if this comes up later in my notes, actually. Wait, that was pretty quick. That feels quicker than it used to be. Oh. That's very quick. Wow. Wow. Anyway, yeah, there's lots of other content out there to cover particle wave duality if you are interested, and really any of these topics. The second key concept is quantum superposition. Super duper position. A quantum system can exist in multiple states at once until it is measured. For instance, an electron can be in a superposition of being in different positions or energy levels simultaneously. I have so many bombs. I'm gonna see if I can use them to find the secret room first. Oh, I was wondering why the doors didn't open. So many bombs. Please tell me it's here. Yes! Oh, excellent. Key concept number 3 is quantization. Certain properties, like energy, are quantized at this level, at this scale. Oh, it's M! It is a trinket. I won't hold on to it because it scares me. But it is a trinket. Let's go down here first. Excellent. And then go up here. I guess so. It's another trinket. And a black heart. And I have the DPS to deal with this without too much issue. I could also just teleport out of here now that I think about it. Yeah. Yeah. Okay, cool. Now let's face the boss. Let's face the music. So, certain properties, like energy, are quantized, meaning they can only take on discrete values. Electrons in atoms, for example, occupy specific energy levels rather than a continuous range. Well, you're back to finish our fight, I see, after I ran away like a fool. Actually, not like a fool. That was rather smart of me. Oh. At least I get luck. Let's drop you off here and then go get Key concept number 4. I need to pay more attention. The uncertainty principle. Formulated by Werner Heisenberg, this principle states that there is a limit to know how precisely we can know certain pairs of properties, like position and momentum, at the same time. The more precisely we know one, the less precisely we can know the other. I might have enough money in a few rooms. I'll see what's here. Okay. I will keep that in mind. Why does it say I haven't been to the boss room? I mean, I didn't clear it. It just confused me for a moment there, that's all. My nose itches. Why does my nose itch? And what can quantum mechanics tell me about it? Probably not that much. What's it even used for then? What possible use is there to quantum mechanics if it can't explain why my nose sometimes itches? Absurd. The arrogance of science. Yay, key. Key concept number 5. Entanglement. When particles become entangled, the state of one instantly influences the state of the other. Maybe I'll put a little asterisk on saying instantly there, but... Am I normal, Eve? No, I have the horns. I would have been a little upset if I accidentally picked up a heart at some point. Like when I was breaking all the poop, since, you know, I saw there were several hearts in the remaining poop. It's okay. And I will take you moving forward. So again, when particles become entangled, the state of one instantly influences the state of the other. No matter how far apart they are, this strange and non-local phenomenon has been experimentally verified and is foundational in quantum information science. Sure. Who'da thunk it? Good for Huda. She thunk it. Yes. Yes. No. What? Well, I'm not happy about how much health I just gained, and yeah, halved my damage. But that's alright. Oh, I saw that rock. Just a little too late. The final key concept in quantum mechanics. I felt like doing some assonance there. That's all. Is wave function and the Schrödinger equation, which it sounds like two, but it's just one. It's really just one. I couldn't remember immediately whether that only affected my red hearts or what. Hey, get back here. I want to sacrifice you. Normal things to say in a casual conversation. Oh, you're not going to give me damage. But fire rate is still appreciated. No. Oh, yes! I finally killed him fast enough. And I got a key. I am curious, but not that curious. So again, wave function and the Schrödinger equation. The state of a quantum system is described by a wave function. Hold. There. A mathematical function that encodes the probabilities of outcomes. The Schrödinger equation governs how the wave function evolves over time. Quantum mechanics is essential to understanding... Ow. Essential to understanding atomic and molecular structures, chemical bonding, semiconductors and transistors, which is the basis of modern electronics, lasers, quantum computing, and MRI and other medical technology. Some other medical technology, I suppose not all. Is the secret room... Oh, I don't know. I mean, I have the bombs to check. It's probably gonna be down. It was not. Well, color me wrong. That was a strange thing to say, but I'll stand by it, I guess. I don't know. No! I thought... yeah, I was being foolish. Get rid of you. There. Alright, I saved some amount of face in that interaction. Now, let's get into... Oh. Okay, that didn't rocket it into me. That's nice. Let's get into some more technical depth now regarding quantum mechanics. First of all, let's talk about the elephant in the room. That is the Schrödinger equation. Maybe that's not the elephant you were expecting me to talk about. I feel like it is. From what I know of quantum mechanics, which isn't much, the Schrödinger equation is so fundamental to everything. Yay! Yay! Oh. Well, I was gonna blow you up anyway. I didn't want that. That's okay. Now I have more money. I should have maybe saved that for the boss, but that's alright, I don't care enough. So, oh, which do I like more? I don't know. Let me go back and take that pill real quick. I just want to see what it is. It's fine. Okay, well that was kind of disappointing. But it could have been Gulp. You never know. You never know. Ever. Why is there nothing above you? Curious. Well, okay. Not that curious, I guess. I am fast enough to try and attempt this. No, I'm not. That is... Nope, never mind. This is way too far away. Okay, well, cool. Nice. That was a solid hit. Stretch. Stretch. That was such a gross, such a far stretch. So gross. Nice. Right on the money. Ooh, look at that stretch. Good, 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 good. Nice. Woo. Gotcha. And, okay, we're just having revelation on... Oh, yeah, I don't have the trinket. Oops. We're just getting revelation every run now, apparently. That's cool. I'm not opposed. Oh, hold on. Also, I see that. Oh, well. What I really want is this, and I got the bomb back! It respawned when I left the room, and yay! It's already paying off, isn't it? And nothing else on this floor, so we continue. So the wave function, denoted by phi of x and t. It is a function of both position and time. I think it's phi, anyway. Maybe correct me on that. It's been a minute since I've tested out my Greek in terms of math and physics. Phi, phi, fo, fum. That's right. Contains all information about a quantum system. It is again the wave function, that is. It is generally a complex valued function whose square modulus gives the probability density of finding a particle in space. Oh yeah, we're combining all of the past topics in the several recent episodes, because quantum mechanics requires it. Also, oh, right. I feel like I'm waiting for a good opportunity to use that, and then it's like, it doesn't actually matter. I would just rather have it on all the time. So how's your day going? Careful. There. Don't be a full health. Where did the... Hello? Where did the music go? That was scary. Freaky. Whoa. Oh. Oh, you're still alive. I'm trying to read. I really am, but it's kind of difficult right now. Mostly because of the subject matter more than actually the game or the enemies. I am desperately trying to figure out how exactly to say some of these things. Well, yeah, I'll take that. Fantastic. Yay! So the time-dependent Schrödinger equation is given, well, you know, maybe just look this one up. I'm not going to describe it. And in fact, I have described it somewhat recently in the episode talking about I, the imaginary number. Wow, don't mind if I do. How did... Whatever. Oh, great. Anyway, it involves I and Planck's constant and the Hamiltonian operator, which is the total energy of the system. And there's also a time-independent version of the Schrödinger equation for stationary systems. Stationary states of a system, rather. Ow. And again, phi or phi or whatever it's actually called, because I can't fully remember. Oh, again. Wow. Ooh. I would rather have this. Yeah, I think that's the right call. No. Snow? No. My turn. My turn. And we're not missing anything, right? Right? I don't think so. Especially not now. What? Oh. I am at full health. Max health, I should say. Anyway, I didn't... This is more of a technical overview than it is a conceptual overview, so I'm not actually gonna talk very much more about the Schrödinger equation, just that it, represents the state of quantum systems and how they evolve and how energy is conserved over time, and that's why I is part of the equation. So that way it may change sinusoidally, but it may never exponentially grow or decay, But that's all stuff I've covered before. Next, let's talk about operators and observables. The Bible? Seraphim? Not what I expected. That's all. Actually, what am I even doing? I will absolutely take this with me. This is a free kill. At least on this floor. Ooh, that was fancy. Very fancy. Yeah, I'll take you too. So in quantum mechanics... Whoa. Hold. Okay. Oh, you regened. In quantum mechanics, physical quantities, referred to as observables, are represented by Hermitian operators acting on wave functions. Let's just hit that real quick. For example, position is hold on, I'm not fully understanding the intent of this section. I guess it's just an introduction to notation, basically. Ancient recall. Can you give me... Oh. I was hoping for a free The Fool card, and I released it too early again, huh? Ooh, Cursed Skull. No thank you. Yeah, I'm a little confused at the nature of this section that I'm currently reading about quantum mechanics, but... Oh, where is the planetarium? Why haven't I found it yet? Get out here. Where is it? Where is it? Don't tell me I skipped it. Please? Uh-oh. I either skipped it or it's on the next floor. The way I do the floors for the ascent makes it so that the percent chance caps out on Gehenna 2. So, hopefully. Also, where is the skull? I was not paying super close attention. I kind of need it. Is it near the boss? No. There are a bunch of skulls in here, and I want none of them. Not any of those. Not any of those. It is Necropolis 2. Just double checking. You never know. Oh, good. You had me worried there. Anyway, position is given as x hat equals x. I'm not sure why it's listed like that, but whatever. And then momentum is p hat, which is equal to negative I times Planck's constant times the derivative, the partial with respect to x of nothing else. And then energy is h hat, which is the Hamiltonian. Then we have commutators, which is bracket x hat comma p hat equals I times Planck's constant. I guess I'll do this. Okay. Cool. Commutators determine the uncertainty and whether two observables can be measured simultaneously with arbitrary precision. Cool. If I use this, do I keep the health? I do. Well, that was an interesting and unexpected reaction. Very cool. I'll take you, and then I will not use you. Where is the entrance? Good. Next, let's go over the uncertainty principle. Heisenberg's uncertainty principle states that delta x dot delta p is greater than or equal to Planck's constant over 2. If I'm reading that right, I know I've been out of my depth before in some of these episodes, but this, I fear what I am saying. It's a weird way to say it, but it's true. Kind of. So again, it is impossible to precisely know both the position and momentum of a particle at the same time. This is not due to experimental limitations, but is a fundamental property of nature. Why did they both cancel their attacks? That was weird. What do they know that I don't? Well, I went this way. Oh, hi, lasers. Because I figured the shop would be near here. Near the secret room. Also, where's the planetarium? Oh, nuts. Aha! But where's the planetarium? Okay. I mean, sure. Right, greed! I forgot. I totally forgot about the Keeper Sack. That's it, not greed. Wait, I can spend more money if I do this. Sure. Wait, also, I do genuinely want this. And I'm keeping the skull on me to drop, and I'm reminding myself about that verbally right now. Great. Yay! Already helping. There you are. Wait, is this a dead end? No, it's... okay. Okay, cool. Did I really miss the planetarium? I may have. I may just have. That would be so distressing. So mildly distressing for me. I would be so mildly distressed. Okay, that scared me. What's with the lasers over there? Yes, of course I get more money now. Is there anything anywhere else to explore up this way? I don't think there was, but I want to double check. Okay, there was that. No. And I can't buy anything with 11, can I? Well, I can buy you. Oh, not enough. Let's see. Next up, we have quantum superposition and linearity. So a system can be in a superposition of states, and, well, I would read you this equation, but it's less of an equation and more of just a linear combination of wave forms, I guess. And, oh, yes! Yay! Sure. And that's really all it is, that you can add linear combinations of wave functions. Or waveforms. I'm not entirely clear if there's a difference between those. Where, let's see, it's a complex valued linear combination of eigenstates of some observables. Okay. I getcha. I love eigenvalues. I mean, I know that eigenstates are a little different. A little bit, but only a little bit. Unironically. Oh, I need money. I need a lot of money. Huh. Anyway, upon measurement, the wave function collapses to one of its basis eigenstates with a probability given by the modulus of the coefficient squared. Yes. Next, we have the measurement postulate. Ow. That was dumb of me. The measurement postulate states that every observable corresponds to a Hermitian operator. That was a bit of lag there. Very interesting. Very interesting. Is it my rock? No. It's the game that's lagging. I got 2 skull hats? Okay. I need money! Oh, cool. It drops it for me. Thank you. I need money! I need funds! Oh, great. Okay. Phew. Oh. That could have been bad. It's also rather bad that I'm taking a lot of hits, but that's okay. It's more okay than not having money. Imagine being poor. Ugh, gross, couldn't be me. Anyway, again, every observable corresponds to a Hermitian operator. The result of a measurement is one of the eigenvalues of that operator. And again, lag. And again, risky movement maneuvers I could just simply move through. Because I am born to rock again. Oh well. Lag! I don't care enough about that. I'll go blow that up, actually. Yeah, it's the right thing to do. The responsible thing to do. That's close enough, right? Yeah. Yeah. Oh boy. Camelocria it is. Neat. At least I have a very good fire rate. Give that to me. So, still talking about the measurement postulate, we have that if A hat times phi equals... No, not phi. This is definitely phi, but it's the fancy physics phi. That's why it's confusing me. That's why I feel like I can only partially recognize it. Anyway, if a hat times phi equals lowercase a times phi, implying that the first one is uppercase, which it is, then phi is an eigenvalue, lowercase a is a possible measurement result, and the system collapses into phi after the measurement. Hope that makes sense. Next, we got quantum tunneling. Yeah. Particles have a non-zero probability to cross a potential barrier. I am freaking out. Even if their energy is less than the barrier height. A purely quantum effect. In other words, they can teleport through walls, kind of. Ow. Yay, I ate him. I ate the lava worm. Yummy. Careful, careful. There we are. I'm getting tired, boss. But I will continue, nonetheless. With the same energy as before. Oop, there we go. For example, a particle incident on a potential barrier, V of x equals 0 if x is less than 0, equals V naught if x is between 0 and A, not alpha, A. Hold on, I have computing to do. Where could you be? Not any great locations, so I'm just gonna guess. Cool. The sharp plug! Wait a minute. Yay! A little more damage, just slightly. It's fine. There you are. And again, V of x is 0 for x greater than A. Did I say that final part? Whatever. Even if E is strictly less than V naught, there's a non-zero probability that the particle emerges on the other side. Next, we have the concepts of angular momentum and spin. Spin to win. The only spin I know. That's not true. Operators. L hat x, L hat y, and L hat z, and total angular momentum. L hat squared, or what we're working with here. Commutation relations between some of these include L hat x and L hat y. Commutating, I guess, is that the verb for it? Equals I times Planck's constant times L hat x. And L hat x commutating with L hat squared equals 0. Don't ask me what that means. I have no idea. Oh. Hi. Even when I ask someone to explain it to me. I'm tempted by Dunce Hat, but Infamy is pretty good. Also, I only just now realized that on the last floor I basically gave away not just my strength, but my ability to open the item room. Good thing I didn't... A good thing I found some pennies on this floor. And I see two, at least, very good locations where the red room could be. Actually, for real this time. Not just wild speculation, because there's nothing good. And just want to confirm, yet I have two more. Let's try over here first. Bomb delivery service. Okay. So it's not down there, so I'm gonna try the staircase-looking structure on the left. No? Then where is it? Ugh, maybe I should have gone straight down from here. Oh well. It's fine. I'm only a little upset. Oh, wait, there's a third staircase right here, isn't there? Yeah. Yep. It's probably diagonally up and to the right from this room, then. Or even two up from this room. A lot of good places it could be. A lot of very good places it could have been. Anyway, let's talk about spin. Spin is intrinsic angular momentum with no classical analog. Which is pretty weird for people. You hear the term spin, and I mean, in a way, it's kind of, sort of like spin, but not really. Now when you get down to the nitty-gritty of it. I know that much. Yeah, I'll do it. So, for example, like, when we think of spin, we think something spins either clockwise or counterclockwise, and that's it, and maybe there's like an, you know, a rotational velocity, how fast something is spinning, and that's kind of it. With quantum particles, such as electrons, for example, you have spins of 1/2, because actually this doesn't really relate to physical spin. So, spin 1/2 particles, such as electrons, have two eigenstates, up and down. This is represented using Pauli matrices. Sigma X, Sigma Y, and Sigma Z. I don't know what that means, but, you know, it's a specific enough name that you could go look it up yourself. If you want. Nice. Next, we're talking about entanglement and non-locality. Whoa. Scary. Oh, good. I saw that I was able to get inside the rock to break it. So two particles are entangled when their states are not separable. Phi AB is not equal to phi of A. I'm not sure what the proper English word is to convey this operator, but phi of A combined with, or compounded with phi of B, I guess. That's my best attempt. I mean, it's sort of a cross product or set union sort of deal looking. Kind of. Sort of. Oh, just my luck. Then we have the EPR paradox and Bell's theorem, which shows that quantum mechanics allows correlations between particles that cannot be explained by local hidden variables, and this has been confirmed experimentally. That's very interesting. I might look into that more myself. I've not heard of that. Cool. We've got just a few more of these left. Next up is identical particles and quantum statistics. We have the symmetrization principle, which features bosons, symmetric wave functions. Multiple can occupy the same state. For example, photons. I guess I'll keep the stud finder. Then we have fermions, which are anti-symmetric wave functions that are subject to the Pauli exclusion principle. For example, again, electrons. Where are we going? Are we there yet? We're going here, that's where. Ow. Well, there's a full health next floor. It doesn't really matter. I just want your pennies. Happy Pride Month. The implications of the symmetrization principle gives rise to atomic structure, such as electrons in orbitals, the Bose-Einstein condensation, and the Fermi gases in solid-state physics. Blank rune. I can't hurt, right? Next, we have perturbation theory, which is used to find approximate solutions to systems where the Hamiltonian is slightly modified. So, h hat equals h hat naught plus lambda times h hat prime, where h hat prime is some small perturbation away, lambda away from h hat, basically. I mean, I'm pretty familiar with perturbation theory, it's pretty cool. Applications include the Stark effect, which is the electric field on an atom. The Zeeman effect, which is the magnetic field on an atom. I'll get healed in the next phase anyway, it's fine. Yeah, no doing that. And lastly, the fine structure of hydrogen atoms. Next, we have quantum harmonic oscillators. The Hamiltonian is given as h hat equals p hat squared over 2m plus 1/2 m times omega squared times x hat squared. Energy levels are E sub n equals n plus 1/2 times Planck's constant times omega for n equals 0, 1, 2, etc. This models small oscillations in molecules and appears in quantum field theory as the basic mode of each field. Come on, give me more food. I'm hungry. Oh, thank you. Perfect. Yay, I'm full. No, I'm full. Okay. Good. Then, lastly, the final one is measurement and the quantum classical boundary. So where does quantum end and classical physics begin? Wait, I can... Right. Oh, I forgot about that. I can just pick them up and use them. Oh, I forgot about that. Oh, that's such a niche mechanic, but it's so cool. Oh. Anyway, the measurement problem is that the wave function evolves smoothly, that is, unitarily according to the Schrödinger equation, but appears to collapse during measurements. No, I do not know what that sentence meant. That was very loud in my ear, thank you. And there are various interpretations to help explain this, such as the Copenhagen interpretation, which states that the collapse is real but unexplained, the many worlds hypothesis, which posits that there is no collapse, instead all outcomes occur simply in branching universes. There you are. And the decoherence interpretation, which is that the apparent collapse is due to environmental interactions, which is, I think, what I subscribe to. And that will do it for talking about quantum mechanics today. Do I feel as though I've learned anything at all? I'm not sure, because I'll be honest, most of this went over my head, but you know. Being a person familiar with math and physics and everything, I feel like I was able to at least understand more of it than I initially expected. And that is it for Eve, which means next time, ignore the music, we got the blue baby. Only 4 left because Cain is already done. 4 left, and that was the final time of playing Eve. So sad, so sad. Anyway, thank you so much for watching. I hope you enjoyed. I hope you learned something about quantum mechanics, and I hope your brain isn't as fried as mine is right now. Ha 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 ha. So thank you so much. I hope to see you again tomorrow. I need to stop repeating myself in these outros. Take care.